Hi everyone, I'm Jiamu Huang, I'm a second-year PhD student working with Joe Hanawi in the Enigma group. And also I want to point out Elia Pizzati, who's working closely with me on the clustering measurements. So today I'm going to talk about measuring the dark matter halo masses with clustering analysis using the JWST quasar. And why dark matter halo masses? Because Joe doesn't really like stereo mass. And here you see this really nice image of a 2D spectra taken with JWST wide field slitless spectroscopy. And here you see two osier emitters, actually an osier emitter pair, at redshift around 6.1. So here you see this clear 5008 emission line. That's just to demonstrate what JWST can see. And since, thanks to Elia and Peter, gave a really nice introduction and results on the motivation of clustering, I don't really need to spend much time on it. So just jump directly into the data. So the data I'm using is from ASPAR project. So what it does is to point on 25 quasar fields and look for osier emitters using slitless spectroscopy. And this is a really nice compilation made by Figure 1. So we can see a stack of osier emitters arranged for different redshift. And what's most spectacular is that we see this overdensity around the quasar that we're looking at. And this is roughly at redshift 6.6, and that's exactly what the redshift quasar we're looking at is. And on the left, showing the number counts, or the number of osier emitters for different quasar fields. So I mentioned there are 25 quasar fields, so we have 23 and 2 that we're still working on. And from this, we can see that there's a very large variation in the number count field by field, and that's showing the cosmic variance is large, and the blue shows the total number of osier emitters in each quasar field, and the red one showing the number in the quasar environment. And from that, we can infer dark matter halo mass, but wait, I mentioned that the cosmic variance is large. How do we do that? It's because we have a simulation, dark matter only simulation, and from the simulation, and apply a really simple assumption of step function halo occupation distribution, meaning that there will be a galaxy or a quasar if we have a minimum mass of the halo larger than some threshold. And from that assumption, we can generalize realizations. From realizations, we can just find the correlation function really easily. On the other hand, we have the observed data, and from that, we compute the correlation function. And this sounds easy, but not really easy to do because we have complicated selection function. But from the data, how do we infer halo mass? The answer is to use simulation to generate covariance matrix. And this encoded, so the cosmic variance already encoded in the covariance matrix. And from the covariance matrix, we can compute the likelihood, and then we infer dark matter halo masses. And here are the results. Before that, I want to mention that since cosmic variance is large, we need to emphasize that we need a proper cosmic variance. And it's showing that the traditional Poisson error underestimate the error budget by a factor of 4 to 5. Here's the results, and the same argument as Elia made earlier. We can find the duty cycle to be 0.26%, which is very low, and that gives a quasar lifetime of 2.3 million years. And what does this imply? So two possibilities. One is the obscured phase, that the large population of black hole grow in really obscured phase. And the other possibility is that radiative efficiency is small. And this gives us a large room of having rapid mass accretion if we assume like a fixed Eisenstein. Thank you.